Hello, once again I am here to explain you or expose a beauty of complex numbers to all the students of 11th standard. Last lecture, if you have gone through it, you will realize that the last thing that I discussed is the operations on complex numbers. I told you that mathematicians have one fantastic hobby. They create new numbers. They are not just happy with creating numbers, they want to play with them. And their method of playing is always same. They want to add them, they want to multiply them, they want to divide them, they want to create equations out of them, they want to define when the two numbers are equal and all that. Once they have defined all that, the game becomes thicker and interesting. So this is what has happened last time. We have learned how to add complex numbers, how the two complex numbers can be equated, how to add them, how to multiply them, how to subtract them, how to divide them, right? So this is what we have seen, and then I have done some problems also in the last lectures, which will illustrate the basics of the complex numbers. Now, I am going to look at the different aspects of the complex numbers. Always remember, a lesson which is visual in nature is always remembered for a very long time. So it should have a visual appeal. So therefore, we try to picturize, we try to, instead of imagination, we try to picturize what are the complex numbers and how they look like, So for that, we have to use certain geometrical diagrams, right? The diagram that we use for representing complex numbers is like this. I think you are quite familiar with this picture. This horizontal line is obviously going to be x-axis. But in complex, now, this is called complex plane. This is called complex plane. So x-axis, or it is called real axis, because it represents the real part of complex numbers, okay? And this is called imaginary axis. Now, imaginary axis is actually, this is the y-axis in normal terms. Here the imaginary part will lie. So for example, and this entire plane is called complex plane. And all the diagrammatic representations of complex number and its operations are altogether called Argand diagrams. So whenever you are trying to relate any complex operation in terms of figures in this particular plane, then that picturization will be called Argand diagram. So it's a complex plane where the x-axis represents the real part and y-axis represents the imaginary part. Just take an example. Suppose I want to represent x is x plus iy to be equal to, say, 2 plus 3i. Very simple. Okay. So 2 plus 3i, actually this 2 and this 3 are never going to mix up. They will always remain set. So this is actually equivalent to an ordered pair 2, 3. So ordered pair 2, 3 means what? X coordinate is 2, y coordinate is 3. So if this is 1, this is 2, this is 3, this is 4. Here also it is 1, this is 2, this is 3, this is 4, right? So now I want to represent a number which has the coordinates 2, 3. So 2, 3 means this is the number, this is 2, 3, so here it will be here, right? This is 2 and this is 3. So this number will be 2, 3. But in ordinary coordinate geometry, we'll call it 2, 3. But in complex numbers, we call it 2 plus 3i, right? So these two representations are actually same. This is called Cartesian representation. This is called complex representation, okay? So it's very simple. Now, remember one thing, this complex number can also be explained in terms of vector. So if you have heard vectors in physics, then you will be familiar with this concept. In mathematics also we are going to learn vectors, but it will take some time for you. But I am just borrowing something that you have already learned in physics. So actually this complex number is represented as a vector. This vector starts from the origin O and it reaches this point A, right? So this vector OA has got two components. One is real component and another is imaginary component. Real component is 2 and imaginary component is 3. So this is 2, this distance is 2 and this distance is 3, right? So therefore this distance is 2, this distance is 3. So this complex number or this vector is 2 plus I3, correct? So that is how the complex number can be represented. This is called Argand diagram, okay? Now if I want to represent the addition, see, it's very interesting. I told you in the beginning itself that complex number is not at all complex. It's very beautiful creation of these mathematicians. And let us see how beautiful it is. See. Now, geometrically, if I look at the addition of two complex numbers, how does it look like? Let us see. So this is our y-axis. This is x-axis. This is one complex number. I told you it can be represented as a vector. And then this is another complex number. So here this complex number is, suppose I call it A. It is x1 plus iy1, right? And this complex number is x2 plus iy2, correct? Now that means this distance is y2 and this distance is x2, correct? This distance is y1 and this distance is x1, correct? Now I want to add x1 plus x2. So this is z1. This complex number is z2 actually, and this complex number is z1. So I want to represent where the z1 plus z2 will go. You will be surprised to know that it becomes a law of parallelogram because vectors are added based on law of parallelogram. So you complete the parallelogram. Means what? You draw a line parallel to this line here of the same size, and then draw a parallel line here. So this line is parallel to this line. So this line is parallel to this line. Now here you will get the addition of complex numbers. So this will be z1 plus z2, and it can be obtained by writing x1 plus x2 plus I times y1 plus y2, y1 plus y2, correct? So that is how this complex number, and the diagonal of this parallelogram will represent z1 plus z2. Very interesting. Now similarly, what do I mean by, suppose I have a vector called z1. So this is vector z1, okay? So this is a vector z1, and z1 is what? x1 plus iy1, correct? So what will be minus z1? So what will be the minus z1? Minus z1 according to vector algebra, it is the same vector with opposite direction. So that means the vector will start from here. It will have the same length as that of, so these two lengths will be equal, and only thing is it will be in the opposite direction. So it will be what? It will be minus x1 and minus iy1, correct? So this is be what? If this is z1, this is minus z1, correct? So this vector is minus z1. So if I want to add z1 with z2, suppose this is z2, this is z2, okay? And I want to add z1 plus z2, then I will complete this parallelogram, okay? And I will take its resultant. That will give me z1 plus z2. But if I want to subtract, what will I do? So I will add only, but only thing is instead of adding z1 and z2, I will add z1 minus z2, correct? Or in this case, it will be minus z1. So this is z2. This vector is z2, correct? This vector is minus z1, correct? And I want to add these two vectors. So I will have to complete this parallelogram like this, you know? So this is the parallelogram I have completed, and then I will take this resultant. This will give me z2 minus z1, correct? So addition and subtraction are done by using geometrical diagrams of law of parallelogram, you know. So this is how the addition can be expressed and subtraction can be expressed, okay? So I'll give you a numerical example which will be sufficient for you to understand the concept of this, okay? For example, let us take a very simple example. Let us take a number called z1. which is equal to 1 plus 2i. Let us take another number z2, which is nothing but 2 plus 3i. Now let us draw the diagram of z1 plus z2. We'll also draw the diagram of z1 minus z2. Okay. Where does it represent? How does it represent? Very simple. So let us see. For that, first of all, I will have to draw the Argand plane or complex plane as we call it. So this is a complex plane. This is a imaginary axis. This is a real axis. And my x coordinate do not go beyond 1, beyond 2. So I'll just draw it 1 here. I'll write 2 here. And at the most, I'll write 3 here. So now here also, at the most 3. So it is 1. Then it is 2. Then it is 3. And here it is 4. Correct? So therefore, I want to have a number called z1, which is 1 plus 2i. So 1 plus 2i means x coordinate is 1 and y coordinate is 2. So it will be exactly at the intersection of this. So this corner will give me 1 plus 2i. Correct? So this number is, let us call it z1. So this is z1. Okay? Now 2 plus 3i. So 2 plus 3i, 2 will be here and 3i. So it will be somewhere here. So this is 2 plus 3i. This is 2 and this will be 3. So this will be 2 plus 3i. Okay. So this is one vector, first vector, and this is second vector. Okay. So these are the two vectors. This vector is called z1 and this vector will be called z2. Okay. So these are the two sides of the parallelogram. So I will have to draw another line parallel to this and another line parallel to this, so that this point will become 2 plus 1, this will be 3, and 3 plus 2, this will be 5. So 3 comma 5. Correct? So this will be, everywhere it will be increasing by 1 unit. So it becomes increased by 1 unit, and here also it will be 1 unit. So this will be 3 plus 5, or this number will be called z1 plus z2. Now I want to represent z1 minus z2. So here this is z2. This vector is z2. So in the opposite direction there will be minus z2. Equal in magnitude and opposite in direction. This vector will be minus z2. Now I want to find out z1 minus z2. z1 ends here, right? And this is z2, correct? So this is the parallelogram that I am looking for. This is the parallelogram that I am looking for, right? So this is parallel to this is parallel to this, and then the resultant passing through the point of intersection, So the resultant passing through the point of intersection, so it will be like this, so it will be like this. This will be z1 minus z2. So this is the origin, and from here it starts, right? Like this, right? So z1 minus z2. So if you are getting confused, I will draw a separate diagram for z1 minus z2. Let us see. Okay, let us see. Okay, so this is z1. Let us say this is z1. Correct? This is z1. Let us say this is z2. This will be down below. This will be minus z2. Okay. So z1 plus z2 can be found out by completing this parallelogram and drawing its diagonal. So here there will be z1 plus z2. And z1 minus z2 will be this parallelogram. See? And this will be the vector called z1 minus z2. So addition can be represented by law of parallelogram. Okay. So this is how the addition and subtraction can be demonstrated by using Argand diagrams. Okay. Most interesting part is, of course, not the addition and subtraction. The most interesting part is the multiplication and division and its ramifications in the world of complex numbers. They are very, very important. And before you understand that, I want to introduce some more concepts. Okay. So now let us get rid of this for the time being, so that I don't need this right now. Okay. So I want to introduce one more concept called polar form of complex number. Polar form of complex numbers. What does that mean? That means whenever you draw a complex number in the form of a vector like this is vector, this complex number is z, which is nothing but x plus iy, right? This is the complex number, right? So it has a magnitude and direction. Direction is given by this angle, this angle gives me the direction. This angle is called argument, or sometimes it is also called amplitude. Now argument is in short denoted by arg. So if this number is z, then it is arg z, or it is also short formed as amp z, whichever is suitable for you, but I am going to use mostly argument of z. Argument of z is the angle made by the positive direction of x-axis with the vector representing the complex number z, which is this, correct? So this is the angle argument, and this is the length of the complex number, or the vector representing complex number, that is the magnitude. Magnitude is called mod z. It is called mod z. It is nothing but the distance of the complex number xy from the origin. Now, what is the distance of complex number? Because you all know that this distance is y, correct? And this distance is x. Very clear. So, by Pythagoras law, you know how much is this distance. So, the distance that is mod z of the complex number is nothing but, by Pythagoras law, it is x square plus y square. So, mod z is a x square plus y square. It is called modulus of a complex number. Now, modulus is nothing but the distance of the number x plus iy from origin. That's the simple explanation of modulus. Okay. So, mod z is denoted by root of x square plus y square. That means root of square of real part plus square of imaginary part. So, that is how we define this mod z. Now, what is polar form? Polar form means most of the times this mod z is written in the form of a simple letter called r. So mod z is r is always positive. So suppose this distance is r, right? So we'll call it r now. Mod z is nothing but r. So that from the ordinary trigonometry that y upon r is what? It is sine theta. Opposite side upon hypotenuse is sine theta. Then adjacent side upon hypotenuse is cos theta. Correct? So this gives me a relation like this. Y is equal to r sine theta and x is equal to r cos theta. These are the conversion formulas. From the conventional notation, Cartesian notation, x plus iy, if you want to go to polar form, use this formula where r is given by what? Root of x square plus y square, and theta is this angle. Now, if I take y upon x, what will happen to y upon x? Y upon x will become r sine theta divided by r cos theta, which gives me tan theta, because r gets cancelled. So, I get tan theta. So, y by x is equal to tan theta. So, what is theta? Theta can be written as tan inverse of y by x, right? So, I know theta and I know r. If I know x and y, then I can find out r and theta, because r is expressed in terms of x and y, theta is expressed in terms of y and x. Therefore, I can convert from one type of coordinate system to another. One is polar form, the other is the Cartesian form. So, in polar form, x is equal to r cos theta, y is equal to r sin theta. Any number x plus iy can be written as r cos theta plus I r sin theta. So that means you can take out r common and it becomes cos theta plus I sine theta. This is called polar form of complex numbers. Okay. So this is x plus Iy. Every time writing this sometimes becomes laborious. So we have a short form for that. I just write cis theta. Now cis theta means actually a short form of cos theta plus I sine theta. So therefore this is called the polar form of complex numbers. So I want you to understand that complex number can be written in the form of theta and r, where r is the modulus of the complex number, theta is the argument, and the argument is always measured in terms of the angle from the positive direction of x-axis and towards the vector representing z measured in anti-clockwise direction. Correct? So that is how this whole concepts can be explained. So always remember, what is mod z? Mod z is equal to square root of x square plus y square. And what is theta? Theta is tan inverse of y upon x, right? At least the preliminary information is given to you. Okay. So now this is how the complex numbers can be represented. This is called Cartesian form. This is a Cartesian form, and this is called polar form. So this is Cartesian, this is polar. Okay. So we can always convert from one to another. So let us take an example. So if you have, say, a complex number, let us say z, okay, this z is of the form 3 plus 4i, okay. So what is 3? 3 is the real part of z, okay, which is nothing but, which we call it x. 4 is what? Imaginary part of z, which is what? Y, okay. So now what is mod z? Mod z according to our formula is square root of x square plus y square. Now we know x is 3, so it is 3 square, and y square is what? 4 square. Therefore this is 9 plus 16, which is equal to square root of 25, and the answer is 5. That means r, which is also equal to mod z, is given by 5. Now, what is theta? Theta is given by tan inverse of y upon x. So theta is equal to tan inverse of y, which is 4 upon what? 3. So that is how we can convert from one to another, right? This is very simple. Okay. So this is how argument and complex number, modulus can be represented. Okay. Now comes the most interesting part. If I want to represent multiplication, if I want to represent multiplication, then what is the consequence? How do you represent a multiplication in Argand diagrams? Now, that is also very interesting. Let us see. So here is a y-axis, imaginary axis. This is called x-axis, but x-axis here is called real axis. This is actually y-axis, but we call it imaginary axis. Now, we are going to multiply two numbers. So let us take two complex numbers. One is z1, which is given by x plus x1 plus iy1. There is another complex number z2, which is x2 plus iy2. Correct? Now, I will write it here. Z1 is x1 plus iy1. In polar form, it will be written as r1 cos theta plus I sine theta. Okay. So this will be theta. This will be theta, right? And this length will be r1. So this length will be R1 modulus, right? Now Z2 will be what? X2 plus IY2, which can be written in polar form R2 multiplied by, let us call it cos alpha plus I sin alpha. Very simple. So this distance here will be R2, correct? Only distance, okay? And then this angle is taken to be alpha, okay? Now, when you multiply Z1 and Z2, what will happen? Let us actually calculate the multiplication, what happens in polar form. So Z1 multiplied by Z2, which means R1 cos theta plus I sin theta, correct? This is Z1 multiplied by R2 cos alpha plus I sin alpha, because this angle is alpha, right? So this is R2. So how do you calculate this product? Using our common sense. This R1 and R2, let us bring them together. So R1, R2, fine. Then cos theta into cos alpha, right? So that will be cos theta into cos alpha. Then sin theta into sin alpha. But then I sin theta into I, so I square, so that will be minus sin theta sin alpha, correct? So this will be cos alpha, so real part, imaginary part. Now we have to take the mixed, that means plus I times, now sin theta cos alpha, right? Sin theta cos alpha and sin alpha cos theta. Both are imaginary because cos theta I sin alpha. So it is cos theta I sin alpha and right, like this. So therefore, now this is equal to R1, R2. Now if you are a little bit familiar with this formula, cos A cos B minus sin A sin B gives you a formula for cos of A plus B, right? This is from the trigonometry. So that means this is equal to cos of theta plus alpha, right? And that means this is I times here sin A cos B plus cos A sin B. This is the formula for sin. So it will be sin of alpha plus theta. Okay, correct? Very, very interesting. Now this, what is this? This is argument of, see what is argument of Z1, Z2? Arg of Z1, Z2. Arg of Z1, Z2 is nothing but theta plus alpha. What is modulus of Z1, Z2? Modulus of Z1 is nothing but R1, R2. But R1 is what? Mod of Z1. R2 is what? Mod of Z2. Which means argument of Z1, Z2 is actually equal to argument of Z1 plus argument of Z2. Does it remind you of something of my previous lectures? Yes. This reminds you of logarithm. Log of mn is log m plus log n. So argument behaves like a logarithm, right? But modulus is very simple. Mod of Z1, Z2 is mod of Z1 and mod of Z2. We like this kind of relations which are very simple. But this is not that easy. This is, you have to remember that arguments behave like logarithm, right? So argument of Z1, Z2 is nothing but argument of Z1 plus argument of Z2, and mod of Z1, Z2 is the product of R1 and R2. That means if I want to represent Z1, Z2, where will it be? Obviously, I want to find out an angle which is equal to theta plus alpha. That means if this angle is alpha, I have to take theta degrees further. So if I take theta degree further, then it total angle will become alpha plus theta. So this is alpha plus theta, and the vector will be somewhere here, and its magnitude will be what? R1, R2. That means mod of R1 into mod of R2, and the vector will be here, and it will be apparent. It is like, this vector has been rotated, the second vector has been rotated through an angle of theta. But its modulus keeps on changing because it reaches a larger height because R1 is getting multiplied by R2. So that is how so remember one thing, when you multiply complex numbers, it has a effect of rotating the second vector by the amount of the first vector, by angle of the first vector. अगर पहले वेक्टर का एंगल 30 डिग्री है और इसका 60 डिग्रीज है तो ये नया वेक्टर होगा वो 90 डिग्रीज पे जाएगा. Correct? That is what the meaning of this whole thing. So I'll give you one illustration of this. Say for example, let us take a complex number. Let us take a complex number this is 1 plus I, correct? And there is another complex number, 1 plus I, and let us take another complex number is what, let us say 2 plus I, 2 plus 2I, okay? 1 plus I and 2 plus 2I, okay? So this distance is 1, this distance is 1, okay? This distance is 2 and this distance is also 2. I'll draw a separate diagram. So there are two complex numbers, 1, 1. This complex number is 1. This is 1. So this number is 1, 1. That is 1 plus I, right? On the same straight line, there is another complex number, 2 plus 2I, right? So this is that number. Now, this is the angle alpha, theta, 1. And angle of this is also same, right? So let us find out what is theta. So Z1 is, what is it? 1 plus I. And what is Z2? It is 2 plus 2I, right? So what is mod Z1? Mod Z1, which is R1, which is equal to under root 1 square plus 1 square, which is root 2. And what is mod Z2? It is equal to R2, which is equal to square root of 4 plus 4, which is root 8, right? This can be written as 2 root 2, okay? So this is R1. Now theta 1, what will be theta? Theta will be tan inverse of 1 upon 1. But tan inverse of 1 upon 1 means tan inverse of 1. And tan theta is 1 only when theta is what? 45 degrees. So this is 45 degrees. 45 degrees. Similarly, theta is equal to theta, matlab ye theta 1, theta 2 will be tan inverse of 2 upon 2. So what will be that? That is again tan inverse of 1, which is also equal to what? 45 degrees. Okay? Now, if I multiply these two vectors, this vector with this vector, where will be the new vector? The vector will be adding the two angles. So 45 plus 45. So where will it be? It will be 90 degrees. So it will be along what? This y-axis, right? Now this length is what? This much length is root 2. So this is root 2, right? And this length is what? 2 root 2, correct? So the product will have length root 2 multiplied by 2 root 2. Why? Because that is R1 into R2. So that will be what? 2 multiplied by 2. Therefore it will be length of 4. So this is of length 4, right? And the angle will be 90 degrees. So this vector here, which vector here? It is 0, 4. That means 0 plus 4i, that will be the vector, right? 0 plus 4i, that will be the vector. Because it makes an angle of 90 degrees and its length is 4. And if you actually multiply, let us find out what happens. Z1 is 1 plus I, Z2 is 2 plus 2i, okay? What is Z1, Z2? Let us find out. 1 into 2, that is 2. I into 2i, that is minus 2, okay? Plus 1 into, so I times 1 into 2, that is 2, and 1 into 2, that is 2. Therefore, the vector will be 0 plus 4i as expected. So can you see this demonstration? So always remember that if I take a vector z1 in short, this is z1, this is z2. Now this is theta and this is alpha. Z1, Z2 angle will be theta plus alpha. So it will be somewhere here and it will go on this line. Its magnitude will be product of the two magnitudes. Angle will be theta plus alpha. Okay. Okay, let me explain the diagram, Argand diagram, which can completely represent the division of the two complex numbers. So I want to find out what is Z1 upon Z2. I already explained to you how do you divide the two complex numbers. So first number is what? X1 plus IY1. Second number is what? X2 plus IY2. That is in the Cartesian form. We are not interested in Cartesian form. We are interested in polar form. Fine. So this will be what? R1 cos theta plus I sin theta. This will be what? R2 cos alpha plus I sin alpha. The diagram I have drawn is making it very clear. Okay. So this will be equal to what? I told you that this will be R1 upon R2. These are real numbers, so let us keep it separately and let us take this division separately now. What is it? Cos theta plus I sin theta divided by cos alpha plus I sin alpha. I told you, whenever you are dividing two complex number, all you have to do is take a conjugate of the denominator. What is the denominator? Cos alpha plus I sin alpha. What is this conjugate? Cos alpha minus sin alpha. So I'll multiply by cos alpha minus I sin alpha. And if I'm multiplying, then in order to compensate, I will divide also. Cos alpha minus I sin alpha. Correct? Now, that is how the division is going to be carried out. Okay, fine. So what is this? This is R1 upon R2 will remain outside. And inside, what will it become? See, this is cos theta into cos alpha. Cos theta, cos alpha. I into minus I. So I into minus I is minus I square. I into minus I is minus I square. Minus I square is plus. So this will become plus. Sin theta, sin alpha. So I have taken this into this and this into this. Now I have to take the cross. So that means I'll have to take all imaginary part, right? So imaginary part will be I times cos theta, sin theta cos alpha or cos alpha sin theta, cos alpha sin theta and cos theta sin alpha. But that will be minus sign here. So minus cos theta sin alpha. Correct? Now divided by, very interesting, this will be cos alpha into cos alpha, that will be cos square alpha minus I square sin square alpha. Now this is ZZ bar, so cos square minus I square sin square alpha, which gives me R1 upon R2 is equal to what? Very interesting. This is cos A cos B plus sin A sin B. If you recall from trigonometry, this is a formula for cos of theta minus alpha, right? And this is a formula for sin of theta minus alpha. Correct? So this is the formula for sin of theta minus alpha and this is the formula for cos of theta minus alpha, and denominator gives you what? Cos square alpha plus sin square alpha, but that happens to be 1, everybody knows. Correct? So we got a very interesting result. The interesting result is this is equal to R1 upon R2 multiplied by simply cos of theta minus alpha plus sine of I sine theta minus alpha. Okay. Which means if I want to find out mod of Z1, Z2, Z1 upon Z2, then this mod is nothing but the mod of Z1 upon mod of Z2. Okay. And then, what is the argument of Z1 upon Z2? Argument of Z1 upon Z2 is equal to theta minus alpha, that is argument of Z1 minus argument of Z2. Very interesting. So whenever you multiply, you add arguments. Whenever you divide, you subtract arguments. Okay. That is how the division is carried out. So now this will be, now if I want to represent this complex number, remember theta minus alpha. If this angle is alpha, then I will have to reverse the direction of this angle. So this will become minus alpha. If this is alpha, this will become minus alpha, right? Somewhere here. So the vector will become here. Vector will come here. So it will be the mirror image of this vector along what? X-axis. So this will be x2 minus iy2, correct? So that will be minus alpha, right? So this vector and this vector, if you multiply, but its magnitude will be not this much. I'm sorry. So this will be the vector. The vector will be in this direction. That's all. Okay. But its direction will be compromised in the sense that it is R1 upon R2. For example, if R1 is 1 and R2 is 2, then this will be half. So it will be exactly half. It will, of course, multiply, expand or contract according to the magnitudes here. Okay. So what is important here is this, that these two results, absolutely marvelous. So we have learned one more important thing. Mod of Z1, Z2 is mod of Z1 multiplied by mod of Z2, whereas mod of Z1 upon Z2 is mod of Z1 upon mod of Z2. But argument has a different story altogether, right? What argument does? Arguments behave like logarithm, right? So what is interesting is argument of Z1, Z2 is nothing but argument of Z1 plus argument of Z2, and argument of Z1 upon Z2 is equal to argument of Z1 minus argument of Z2, right? So these are the properties of multiplication and division. Okay. So this is how we understand the complex numbers. Okay. So that's all for this lecture. To next time we will take some problems based on this. Okay.